Hi, how's everybody doing today? I hope everybody's doing well. Great. And today we are going to investigate the experiment number 9 in Labflow, which is determination of the solubility product. Yeah, I'm cold as well. I can see some people are saying a bit chilly, me too. We are already in the experiment number 9. After today, there are only 3 experiments left. Today's experiment is, to me, I hope is going to be for you as well, pretty simple. It's the determination of the solubility product constant of calcium hydroxide. So the objective of today's experiment is to perform a titration of a saturated solution of calcium hydroxide. The titrant is hydrochloric acid, and we are going to use methyl orange as the indicator to get to the end point. And we are going to calculate the concentration of hydroxide ions, and with that information, we will calculate the ASP, which is the solubility product constant. Why I think this experiment should be for you simpler to grab or easier to understand, because this is the last experiment of the titration. You have seen acid-base titrations. So the concept of a titration you already have. Then it's an equilibrium. This is a saturated solution. You have seen equilibrium. You have seen the Le Chatelier principle. So that's why I think hopefully it should be easier for you to do this experiment. So as we always do, I will give a quick overview of the experiment. We will share the page of the write-up of the experiment. Then we'll do some problems, practice problems to make sure you are ready to go to the pre-lab quiz. And then we'll go over the report to make sure you have all the elements that you need to have to complete the report. So let's get started by sharing the page of the experiment. So in the introduction, basically, make it bigger. Here it's talking about that the equilibrium expression for a chemical equation. So here is showing the equilibrium of a salt when you dissolve in water. We dissolved silver chloride in water, and these double arrows are saying that we are having an equilibrium between the ions and the solid. So the equilibrium expression for a chemical for this chemical equation, that is the dissolution of this ionic compound, that is silver chloride, is the solubility product constant. Why is that? Remember that we studied the equilibrium constant. We always say that is the product of the products divided, the product divided by the reactant. But in this case, remember that pure solids are not included. So that's why the KSP is basically equilibrium constant expression for the dissolution of anionic compound. So here is the expression of the KSP for silver chloride. This is something you have already seen. When you have a salt like this, why is the expression here raised to the second power? Because if you always have to write the dissolution. So let's say you have this salt. This salt is in equilibrium of what? Let's look at here. How many silver ions do I have in silver sulfate? I have 2. So the dissolution will give me 2 silvers. This is important, always. Plus 1 sulfate. So when I write the solubility product constant, which is the KSP, is going to be the product of the concentration of the silver raised to the coefficient. So silver has a coefficient of 2. That's why here we raise silver to the second power, and sulfates is 1. So that's why this is the expression. So in order to write the KSP of any salt, first you need to write the equilibrium, the chemical reaction, and then you can write the expression. Any questions there? Okay, so in this experiment, we will determine the solubility of calcium hydroxide here, calcium hydroxide. What are we going to do? We will going to prepare a saturated solution of calcium hydroxide and determine the concentration of hydroxide ions, because we are going to do another titration. We did so many titration, and this is again an acid-base titration. We have the hydroxide, and our titrant is going to be hydrochloric acid. So acid plus a base, we are going to have the salt and water. So once we have the concentration from the titration, from the end point, we calculate the concentration of hydroxide, you know the expression of the KSP. KSP, what is the expression for calcium hydroxide? We have to look at the coefficients, right? So calcium has a coefficient of 1. So it's going to be the concentration of calcium plus 2 times the concentration of hydroxide ions raised to what? I look at the coefficient of the hydroxide ions, and I see that in the chemical equation, I see a 2. So it's raised square. So this is the expression of the KSP. This is what we are going to do today. We are going to prepare a saturated solution of calcium hydroxide. Once we have the solution, we are going to titrate, and we are going to calculate with the titration the concentration of hydroxide. But in order to calculate the KSP, we need the concentration of the hydroxide and the concentration of calcium ions. How is the concentration of calcium ions? We look at the equation here, the molar ratio, 1 calcium to hydroxide. So the concentration of calcium ions is going to be the concentration of hydroxide ions divided by 2. Once we have that, we can plug in the numbers and calculate the KSP. So it should be pretty simple today. Any questions so far? Here is the description of the experiment. We will come back when we do the report. If there are no questions, let's go and move to the practice problems. Kevin, okay. The question that Kevin is asking is a good question. Are you sure that it's simple? It's a very, very good question. Nothing is simple. I think you are probably right. Everything in chemistry requires time. Yes, thank you, Alonso. It's an opinion. Actually, I didn't mean that simple, but what I meant is that it's not a new concept. You have already seen the acid-base titration, so you know what a titration is about. So that is a plus. And then you also have seen equilibrium, and this is just another equilibrium constant that, because it's about a dissolution, they are calling this equilibrium constant solubility constant. So basically, I'm basing on like, it's not a new concept, but yes, let's treat it as if it's not simple. Agree with you, Kevin, because nothing is simple. You're welcome. Okay, so let's go and do share the practice problems. These are the kind of problems that you will encounter in, even in lecture, and at the end of the, you have to do these problems for the report. You have to do the problems in lecture, in a pre-lab quiz. So let's make sure that you have this concept. Whenever you see a problem like this, you will be able to solve it by yourself, like understood. If not, just raise your hand or ask me, because I will be super happy to go over it as many times as it requires. So let's read the problem. Here it says, a 25 ml sample of saturated calcium hydroxide, that's a rate. This is what we are going to have in our experiment. If you were in the lab today, you will be doing this. So 25 ml sample of saturated calcium hydroxide solution, and is titrated with, they are giving us the molarity of the hydrochloric acid. And it says that and the end point is reached after 35.9 ml of titrants are dispensed. So basically the volume of the endpoint is 35.9 ml. And they are asking for the molarity of calcium hydroxide. This is, so let's go over. When you have a problem like this, you read and you say, what is all this about? The first thing that you should do for actually any chemical problem in chemistry is to write the chemical equation. Because if not, you have no idea of the molar ratio or what kind of reaction is happening. So this is an acid-base titration. We know. So let's write the chemical equation. So we have calcium hydroxide that reacts with hydrochloric acid to give you the salt, calcium chloride, plus 2 moles of water. So every time you have a problem like this, you need to write the chemical reaction and balance the chemical reaction. Because in this case, we have 1 mole here of of calcium hydroxide and 2 moles of acid. So that is something that we need to know. Now, they are asking for the molarity of calcium hydroxide. We know that in a titration, what is a titration? You know, at this point, you know what is a titration. You have in a beaker, you have the calcium, you have the base, in this case, and you have a burette, and you are going to add your titrant, is hydrochloric acid. And here you have 2 or 3 drops of the indicator. In this case, is methyl orange. I think they are saying methyl orange. Don't say it. Okay, we have the indicator. Why do we need the indicator? The indicator will change color at the end point. What is the end point? At that point, we don't have excess of any of the reactant. So in the end point means that whatever you had in the beaker, you were adding drop by drop of acid. At the end point, the amount of calcium hydroxide is stoichiometrically equivalent to the amount of hydrochloric acid. Any questions there on what is the end point? Okay, so let me ask you one thing. If I'm titrating 1 mole of calcium hydroxide, at the end point, when the indicator or the solution changes color, how many moles of acid I added? You can send me a message. Send me a message. I will tell you the question again. The question is, at the end point, if in this beaker I have 1 mole of calcium hydroxide, how many moles of hydrochloric acid I need to add in order to reach the end point? Yes, thank you, awesome, excellent, excellent, thank you. Everybody says 2. Exactly, this concept is very, very important because then the calculations are simple. But you need to know what you are doing. You are titrating until the end point. Why you wanna titrate until the end point? Because the hydrochloric acid, that is our titrant, we know the molarity and we know the volume, because I will add, and then record. At the moment it changes the color, I will record the volume. And you know very well that the number of moles of hydrochloric acid equals what? The volume that I used of hydrochloric acid times the molarity of hydrochloric acid. So if we want to know the number of moles of calcium hydroxide, we need to work with the moles of the titrant and then use the molar ratio to calculate the moles of calcium hydroxide. But let's start of calculating the moles of our titrants. So what is the volume of in liters of the what is the value that you have? What is the volume of hydrochloric acid that we use in the exactly? Thank you, Alonso. Awesome. 0.03 59. Because it's 35.9 divided by 1,000. And this is liters. Times molarity. What is the molarity of hydrochloric acid? 0.026 molar. Molar is moles per liter. So the liter cancels, and the number of moles of hydrochloric acid, what is the answer that you have? What number do you get? Yes, very good. Exactly. Thank you. So we obtain 0. Thank you. Awesome. Perfect. Okay, I can write it like that, but it's the same thing. And this is the number of moles of hydrochloric acid. So always in a titration, first you are going to calculate the number of moles of the titrant. And from there, you are going to calculate the number of moles of your solution that is in the beaker. So now, we need to use the molar ratio. The number of moles of calcium hydroxide is going to be what? The only relationship, thank you, yes, yes, that is perfect, exactly, equals the number of moles that we calculated before of hydrochloric acid times, we know that 1 mole, this is the molar ratio of calcium hydroxide, here 1 mole reacts with 2 moles of hydrochloric acid. So if we are going to say, we can say the same as Q-Han just said, you just divide it by 2. That's another way. I just wanted to show you the molar ratio in case you have a different equation. So our number of moles of calcium hydroxide is going to be this number that we calculated before, 0.000933 divided by 2. And these are going to be the moles of calcium hydroxide. But what are they asking here? They are asking for molarity. And that is, once we have the moles, the molarity of calcium hydroxide is going to be what? The number of moles of calcium hydroxide divided by what? What is molarity? Number of moles per, I'm waiting, per what? Molarity. Liters, yes. Thank you, Kevin. So what is the volume that, what number do I write here? Let's read the problem again. Yes, thank you. It says 25 ml sample of saturated calcium hydroxide. So I need to put the volume of the calcium hydroxide because that's what I'm calculating. And that will be in liters, 0.025. So what is the molarity that you obtain in this problem? When I did the calculations, my calculator gave me this number, 0.019 molar. Hope you get the same. Okay, it's not. Let me write it in a different color. Okay, 0.019 molar. So that's the answer for the first problem. Any questions there? Because most of them are going to be similar. So when you have a titration, always calculate the mole of the titrant. Then with the molar ratio, you calculate the moles of the solution that you're unknown. And then from there, yes, Alonso, it's possible. And actually, I did it that way because it's faster. And actually, Alonso is asking, is it possible to use the equation V1M1 equals V2M2? Yes. Totally acceptable. Why I didn't do it? Because over step by step, because some of the students prefer to understand exactly. But if you use this equation, be careful, because remember that actually you have to this equation, let me see, somebody wrote something. No. What if the question asks for the concentration of hydroxide ion? Sure. I'll tell you in a second. Okay, I'll answer question by question. The first question, Alonso, be careful. You can use that if you use carefully, because remember that here you divide it by 2. So that equation works very well when you have an equation like this 1-to-1. But if you have this equation, be careful when you are going to write, do it both ways and you will see the difference. Because if you have 1-to-1, then works. But if you have 1-to-2, I did it that way. But at some point, I divided by 2. Alonso, did I answer your question? Okay, awesome. Okay, so better be careful. If you have that ratio 1-to-2, maybe it's better to do it this way. And then Kevin is asking, what if the question asks for the concentration of hydroxide ion? Okay, so that will be easy. What do you have here? The concentration of calcium hydroxide. What is the concentration of hydroxide ions? When you have, if you look at the formula, calcium hydroxide here, the calcium hydroxide, we said that dissociates in 1 calcium plus 2 hydroxide. So if you have whatever you calculated, you have to multiply by 2 because the concentration of hydroxide, exactly. Very good, Kyuhan. Thank you. Kevin, did I answer your question?
Yeah, well, kind of. It's saying that it's pretty much exactly like the first problem, where it's saying 25 milliliter sample of saturated calcium hydroxide is titrated with, HCl,
Yes.
and then it's asking for the concentration of the hydroxide ion. So it's pretty much the exact same thing as number 1, but it's asking for the concentration of hydroxide.
Then you basically multiply. Kyuhan is writing here the concentration of in the message box. It says, Kyuhan, you are correct. The concentration of hydroxide ion is 2 times the concentration of calcium hydroxide. Very good. Because of this, per one of these, you multiply by 2, and that's it. Because per one of these, you obtain double of this.
Oh, so basically it's the same thing as number 1. I have to multiply by 2 because of the... Okay.
The molar ratio.
Okay.
Yes, it will be multiplied by 2 because of the subscript. Yes, because if we look at this equation here, per 1 mole, we're going to see another problem, but if we have 1 mole, the copper hydroxide is going to separate. It's called dissociate. And it's going to give you, per one of these, we have 3 particles. It's hard to see that. But if you have 1 of here you have 1 and 2 more here. So basically, per one of these, because this is all together, packed together, is going to separate into 3 pieces, 1 of calcium and 2 hydroxide. So that's why you have to multiply by 2. Per one of these, you obtain 2 moles of, per 1 mole of copper hydroxide, you obtain 2 moles of hydroxide ions. Okay, awesome. Okay, let's see the next question. Let's read it. It says the molar solubility of calcium hydroxide was determined to be 0.021 molar. And they ask to calculate the KSP, the solubility product constant. So whenever you have that problem, the first thing you have to do, always, write the chemical equation, always. So I have calcium hydroxide that dissociates, and then this formula, and you say, how many calcium do I have in 1 mole? Only 1. So I write calcium. How many hydroxides do I have? Scripts. It's a 2. So it will dissociate into. This is the first thing. This is a solid. This is aqueous. And this is aqueous. So the expression P is basically the equilibrium constant, like we always do. We did it for different experiments in previous workshops. Yes, awesome. Johan, you are doing awesome. I got the answer from Johan, and that is correct. Okay, so KSP expression. We don't include in the KSP solids or liquids. We don't include that. Kevin, I'm going to ask you if you can mute yourself. I can hear your...
I'm sorry, I forgot to mute.
No problem at all. Thank you. Thank you. Okay, so the expression of the KSP is, we are going to use just this part because we don't include the solids. Remember, in the other equilibrium, we had to do the product if they are not solid or liquid. So the KSP, in a way, that's why I think it's simpler. It's just the product of the ions. And if they have a coefficient, we raise the concentration to the coefficient of that ion. Calcium doesn't have as a 1, so we ignore it. It's like if we put a 1 here. And the second ion is hydroxide. And we look at the coefficient as a 2. So it's going to be raised square to the second power. So that is the expression of the KSP. So this is the first thing we are doing. Now, what information they are telling us? They are telling us the solubility. What is the molar solubility? Basically, what is the maximum amount of moles that are dissolved, the maximum amount of moles that you can dissolve in a liter of solution? If you add more, you are going to have a solid. It's basically you have a saturated solution. So the molar solubility is the number of moles of calcium hydroxide, the maximum amount of moles of calcium hydroxide you can dissolve in 1 liter of water. So then let's say initially, we have any amount, right? But in the equilibrium, or let's say, we have an amount of, let's say, we can say S. This is the solubility. And we know that if we started here, if S was dissolved, here, because we have a coefficient of 2, we are going to have 2S. Everybody can see this from the solid, because this is hard to grasp, but I want you to see that if we have a solid and it's going, part of it is going to dissolve from 1 whole mole of this. If this is the solubility, we get S. Here we get double of S. The concentration of hydroxides is going to be double because of this subscript. Everybody sees that? Okay, so the first thing is S and 2S. S, we know, is this number, 0.021 molar. But now we have to put it in the equation of KSP. So the concentration of calcium, a nice table, it says, would a nice table apply here? Would apply, yes, but we don't know how much we had at the beginning. So answering to your question, we don't know how much. All we know is that we have a solid here. You can if it helps. But the part that is important is that if this is the molar solubility, then it's double for the hydroxide ions, because we don't have any more information. So all we have to do is, what I'm trying to point out is that you need to look at the S and the 2S, at the coefficient of calcium hydroxide. If you know 1 mole of and double of hydroxide, then you write the expression of the calcium times hydroxide ion square. What is the concentration of calcium? We said is S. And what is the concentration of hydroxide? We said is 2S. This is the concentration of hydroxide. But 2S is square. Everybody sees that? Good, thank you. Okay, so then all I'm doing is, instead of hydroxide, I write 2S. And here I write S. And then I just plug in the numbers. The KSP is going to be 2 squared is 4, And then S raised to the third power, because 1 here and 2 here. And what is the number that you obtain? Johan gave me already the number. Exactly. S is 0.021. Exactly. So this one is what they are giving me, the molar solubility. So the answer that I have is 3.7 times 10 to the minus 5. Don't hesitate to ask me, because you will see some problems and I would like you to be able to solve them all. Any questions on this problem? So this would be the answer. So then we'll move to the next one. It says, how is the solubility affected for the following endothermic dissolution at equilibrium? So I have a solid that is zinc hydroxide. It's a solid. And basically dissolves zinc ions and 2 hydroxide ions. And I have that solution. And they are also telling me that is an endothermic dissolution. What does that mean? Endothermic, remember, if it's endothermic, means it absorbs heat. So heat I need to add heat. Exactly. Yes. Thank you, Kyuhan. That's awesome. Awesome. So here, for now, all I did is reading the problem and trying to understand and try to have all the information. They're saying endothermic means it requires heat, and heat is on like a reactant because it absorbs heat in order to make the dissolution. So the question is, what happens if I add hydroxide, sodium hydroxide? You know that sodium hydroxide is a strong base and is going to dissociate completely into hydroxide ions and sodium ions. So what happens if I add sodium, I add hydroxides? Yes, solubility decrease. I have hydroxide as a product. Remember the Le Chatelier product, the Le Chatelier rule. If I have hydroxide and I add more hydroxide ions, the equilibrium is going to shift to the left. If the equilibrium shifts to the left, means the solubility decrease. Everybody sees that? Decrease solubility. Because the equilibrium shifts to the left. Now what happens if I add hydrochloric acid? I look at the reaction and I look at where are the acids. Here, no acid, no acid, no acid. And at the beginning, I'm going to say, the acid won't affect the equilibrium. No, no, it will affect, even though it's not in the equation. Why is that? Because the hydroxide always a base reacts with an acid exactly to make water. So if I add hydrochloric acid, it's going to react with this, and the equilibrium will shift to the right. It's like remove, instead of adding hydroxide ions that decrease the solubility, is the opposite effect. It's basically removing hydroxide ions, so the equilibrium goes to the right and is going to increase the solubility. Any questions so far? Okay, now what happens if I add this solid? Zinc hydroxide, no effect. Awesome, Johan. Exactly. Remember, adding a solid, it will never affect the equilibrium. The pure solids are not included in the equilibrium. So this is no effect because it's a solid. Don't let this problem trick yourself. And how about the last one, increasing temperature? That one you can tell me. Increase solubility. Very good. They are telling us that it's an endothermic reaction. That means the heat is like a reactant. And increasing the temperature is like adding heat to the system. And adding heat is like adding a reactant, and the equilibrium shifts to the right. And if the equilibrium shifts to the right, means increase the solubility. To the right means increase solubility. Any questions with that problem? Okay, so then, let me see if there is another. No, then we'll go to the report and make sure it's not that long, it's not a pain in the neck. I hope so, but that's an opinion, like we said before. So let's share the page of the empty report. Okay, you shouldn't do many calculations. So there is a page that you will have with all the data, and I believe you can pick any data within that range. I pick this data, you can pick any data. So they will give you the concentration of the acid, and I believe that is the same for everybody. But it doesn't matter though. I think mine was 0.05 molar, but everybody can have a different one. So this is basically the first thing that you have to do. They are telling you the initial, they are doing 2 trials, 2 titrations. And what is the titration? Is what we've been talking before. The titration of a saturated solution of calcium hydroxide. So basically they have the burette and they tell you the initial reading and the final reading. So basically, initial reading, let's say here, and then final reading. So what is the volume if the initial reading is 1 and the final reading is 12? What would be the volume added? Yes, exactly. 12 minus 1. Very good. So here, thank you, perfect. So this is easy It's just final minus initial. You do the same with the second try. It's the temperature they will give you. And then they ask you for the average volume added. That is easy peasy. Basically, let's say you have another number here. Is this number plus this number divided by 2. Just the average of 2 trials. And then they will ask you for the concentration of hydroxide ions. So then you can actually use the equation that you made before, Alonso. You can use that one because they are asking for the concentration of hydroxide. So you know that 1 hydroxide will react with 1 mole of the hydrochloric acid to give you water. So you can basically do, you know that the volume of the hydroxide times the molarity, in this case is 1:1. Molarity of the hydroxide is going to be the volume of the hydrochloric acid times the molarity of the hydrochloric acid. So you can make it actually much simpler like this, instead of going through the way we did the problem before, because it's 1 by 1. So in our case, we are asking for the molarity of the hydroxide. So you will do here, the molarity of the hydroxide is going to be, in my case, the volume that you use of the hydrochloric acid. You will use the average, so you will use this, the average volume of the hydrochloric acid. And then, what is the molarity of the hydrochloric acid? Obviously, it's given at the beginning. Mine was 0.0. We always know the molarity of our titrant, and then divided by the volume of the sample. You have to, if you write this volume in ml, then you write the other volume in ml. In my case, I use 25 ml of sample. You have to read your procedure and make sure you also have 25 ml of calcium hydroxide. And the volume, in this case, mine was the average. Mine was, I think, 11.25 mLs. Either you write both in mLs, it's okay, because they cancel out. And then the concentration of calcium, that is easy peasy. The concentration of calcium is going to be the concentration of hydroxide divided by 2. This way we have to multiply. So the volume we use is the average volume. Yes, exactly, is the average volume. So here you get a trial 1. You're welcome. Trial 1 and trial 2, I think I had 11.50. And then here they ask you for the average, and that's the one you are going to use. That is correct. So for this part is easy. You can use even this equation, and then it says we use the balanced chemical equation for dissociation to relate the moles of calcium to hydroxide. And that's how we got that the concentration of calcium is half the concentration of hydroxide ions. Any questions so far?
Yes. The part where you do The part where you multiply or divide by the volume of hydroxide?
Yes. I don't divide by the volume of hydroxide. I divide by of the sample of calcium.
How do you know if your sample's 25 milliliters or not? Like, is
Okay,
all of ours 25?
Mine was, I think it's either in the data or read in the write-up in the we can go back, read in your in the procedure in the lab report.
I'm trying to find it. I'll talk to you about it later, but I'll just
Okay, sure. Look at this. If you read a part B of the procedure, it says empty the sat in the part B, 0.7. It says empty the saturated solution in the 25 ml volumetric flask into a clean. So basically you are measuring 25 ml of sample.
okay.
So it seems that everybody will have 25 ml of sample. And yes, that's what you are going to have. Everybody will have that.
Okay.
Yeah, okay. Then where are we? Number 2. So the report is short, luckily this one. And here, there are some questions. I wonder if you want me to go over this.
Yes, please.
Okay. So let's look at the first question. Let's read the first question. It says a hydrochloric acid solution has a concentration of 0.09714 molar. So they are giving the concentration of the titrant. And then it says 10 ml of this solution. Okay, no, this is different. Okay, 10 ml of this solution was then diluted to 250 ml in a volumetric flask. And then it looks like the diluted solution they used to titrate silver hydroxide. So let's look at the first question. Let's see here. Where is this first question? Okay. Let's see if I have it here. No, it looks like I don't. But that's okay. I don't need it. Okay. So let's look at the first question. What is the concentration of the diluted hydrochloric solution? Okay. So basically this is just a dilution. You have learned a dilution. You started with 10 ml of hydrochloric acid and you diluted to 250 ml of hydrochloric. It's just a dilution. So what is the equation for a dilution? Again, the same thing. Volume times molarity. In a dilution, initial volume times molarity of the final, right? But what we want to know is the concentration of the diluted. So we have a volume, we diluted to 250. So the molarity of the diluted hydrochloric acid is going to be the original volume. What is the original volume? I started with. Yes, thank you. 10 ml What is the original concentration? 0.09. Thank you. Yes. Awesome. Divided by, what is the volume? The final volume. Yes. Thank you. 250. Awesome. So I got a so this is the first part. What is the concentration of the diluted hydrochloric acid? It's basically just the equation of the dilution. Any questions there in the first question? Okay, so then the second question, they are telling us that for sig figs, do we write the answer? Okay, what's sig figs? Here is a question. How many sig figs? Well, you have to look, you have a multiplication, right? And you look. The number 10 has 4 sig figs. Here, how many sig figs has the molarity? Also 4. How many sig figs has the volume here? 1, 2, 3, 4, 5. So we look at the lower number of sig figs. Our answer has to have 4 sig figs. Did I answer your question? Awesome. Okay, so let's look at the question. It says 7.93 mL of diluted hydrochloric acid was required to reach end point. What is the concentration of hydroxide ions in solution? So the first thing I have to do, always go back to the question and think about the reaction. If we don't write the chemical equation, we don't know what we are talking about. So what they are saying here is that they have a solution of silver hydroxide and they titrate it with hydrochloric acid to make silver chloride plus water. So this is the equation, and what they are saying is that how much they titrated, let me write with another one, 250 mL of this solution, it's written here, was then used to titrate 250 mL of saturated silver hydroxide. So we know the volume, the sample that we are titrating, right? And then what else we know? We know the molarity of the diluted hydrochloric acid, which is this number, let's say M. The number that you got here, the concentration of the diluted hydrochloric acid, and you know the volume also. That is 7.93 mL. So this would be very simple. What is the concentration? We know that the volume, again, the same equation, times molarity of the silver hydroxide equals the volume of the diluted acid times molarity of the diluted acid. So the concentration of hydroxide we know is 1 to 1. So the molarity of the silver hydroxide is going to be what? Who can give me the number? The volume of the hydrochloric acid times molarity divided by the volume that we have here. If I'm going to write mLs here, I will write here mLs as well. That is 7.93. Any questions here? Again, it's the same thing, always. Because this is 1-to-1, I'm using this equation. This is one hydroxide with one acid. And then what is the difference between 2 and 3? Is there any difference between the question 2 and question 3? Yes, exactly. This is correct. There is no difference. Exactly, exactly. So basically, because everything is 1-to-1, one silver and one hydroxide, here it says, what is the concentration of hydroxide ions? It's going to be the same as the concentration of silver hydroxide. Basically, it's a saturated. It's basically, let's do it in a different way. The concentration of silver, because we cannot include, to be strict, we cannot include the solid, so we can say that the concentration of silver equals the concentration of hydroxide, because the coefficients are 1-1. So the question 1, no, the 2, it says concentration of hydroxide. Okay, we calculate it here. We can say, instead of writing silver, let's say hydroxide. Do it directly for hydroxide. It's a better way. And then what is the concentration of silver? The same, because it's 1-to-1. Any questions there? 2 and 3 are going to have the same answer. And let's look at the number 4. What is the KSP expression for the dissolution of silver hydroxide? Awesome. Yes, thank you. D is the answer. Everybody sees why D is the answer. Awesome. Awesome. Because we done with exponents, and if you don't have any questions, I will stop the recording. I want to thank everybody for being here, and I will stay because I want to tell you, well, first of all, I need to take a leave of absence, and the last 3 workshops, you only need to go to do 3 more workshops, and I will, the workshops will continue. And Michael DePaul, you probably know him from the Science Learning Center. He will do the last 2 workshops of the year. He is an amazing tutor. He is he's been in the Science Learning Center for a long time. Everybody loves him, and you are in excellent hands. You will be very happy with him. And I'm really sorry that I couldn't complete this year, but I had some problems, and I really need to travel. My mom is sick, and I need to help her. So, as I said, I will conclude this workshop and stop the recording, but I'll stay to answer all these questions, all the questions, and talk to you.